In this video, I want to talk a little bit about how we can ramp up the reactivity of esters. There's actually two ways that we can do it, and we're going to deal with just one way in this particular video. So just to remind you that what we've looked at in the past so far is where we have something that's an ester. So here's an example of that, where the nucleophile adds to the carbonyl, and we get our tetrahedral intermediate, and the OR minus needs to leave. Now, we've always looked at that and we've recognized that that is actually a terrible leaving group. It's an O minus, which is not a good leaving group in any way, shape, or form. And so there have been a number of little tricks in terms of how we get to the particular product at the end, which would look something like this. And so we have this O minus, which is the big problem. So when we do this, the reactions work, and that's fine, and there's very good reasons for it. You can go and look at those other videos, typically because there's some sort of acidic H that this gets to pick up at the end, and so everything neutralizes and the equilibrium lies towards the right. However, the problem with those reactions is we always needed to use a very good nucleophile. That's fine if we've got a good nucleophile. For instance, we can use a Grignard reagent, excellent nucleophile. And we could use an amine, which was kind of like the limit at which would get a reaction onto an ester. However, if we wanted to use an oxygen, we needed to add an O minus in order to kind of get that reaction to occur. So one of the solutions that we can do is, it's really this OR prime, which is the issue. And what we need to do there is we don't want it to be an OR prime. We want it to be a good leaving group. So we want some kind of leaving group over there, and which is much better than the O minus over there. And one of the easiest ways, the best way that everyone does in the literature, is the leaving group becomes chlorine. And so what we get is a new functional group for you guys, which is known as the acid chloride. And we all know from chemistry that chlorine is a very good leaving group because it is the conjugate base of a strong acid. However, many of you will be looking at me and saying, just be careful here, Prof, because you've told us that a leaving group must be only a leaving group if it is on a carbon that is sp3 hybridized, and this is not sp3 hybridized. So how can it be a good leaving group? Well, it can be a good leaving group because it's not going to do an SN2 reaction. We are going to do all the reactions that we do on carbonyls in exactly the same way, and that is when the nucleophile adds, we need to first break the pi bond, and then we're going to get an sp3 hybridized carbon, and the chlorine can leave. So let's watch what will happen. And the beauty of this type of reaction using an acid chloride is that we can use now very, very weak nucleophiles. In fact, just a simple alcohol is good enough to react with an acid chloride. So let's take an example and watch the mechanism of this to see how this occurs. So I'm going to take just again, a generic type of alcohol. We don't need to draw in what that is. It could have been methanol, ethanol, or some other really complicated molecule. It doesn't really matter. But we've got an alcohol over there. And typically, and this is also important, is just to realize, and you'll see now where in the mechanism, we typically have a weak base that is present as well. So when I did this type of reaction, my favorite base in this one was pyridine. But triethylamine is also something that can work as well. So just remember that pyridine looks like this. All right, so we need a weak base, and what happens in this reaction is that because this is so reactive, we don't need to activate this alcohol in any way. The lone pair of electrons, even though they are not strong, they are strong enough to be attracted to the carbon of the carbonyl of the acid chloride. This carbonyl carbon is super activated because of that chlorine, which is more electronegative, all right, than the carbon that's over there. So that activates this functional group. It makes that carbon over there a lot more delta positive, and by making it more delta positive, it's effectively weakening that pi bond even more, and that means that this can be attracted in there, even though it's a weak nucleophile, can be attracted in over there, and we can break that pi bond. And the net result of that is our tetrahedral intermediate, so we can have an O minus. We've got our chlorine, and we've got our O, here's the R prime, and we've got this plus over there. Okay, now that's really important. Don't forget about this H, because when we did this reaction, the H had not gone. And at this point over here, one of two things can happen. And it doesn't matter which way around you do the mechanism, it's totally fine. But it's at this point that people typically now bring in the base, all right, the pyridine, which can then pick up this proton over here and kick that in over there. And we get our next tetrahedral intermediate. Not much has changed. All we've done is deprotonate, and we've now got the OR prime like that. So let's just follow with all our colors, fill those in so we can see where everything has ended up. The nucleophile is this over here. So there's our nucleophile over there, and we've now lost that H. It is protonated onto the pyridine. I haven't drawn that part out. At this point now, we can see, because we've got this tetrahedral intermediate, we know that this O- over here wants to kick back in, and something has to break. And at this point, it should be very, very clear that it's the chlorine that is the best leaving group by a long shot. This breaking a carbon-oxygen bond, you're going to kick out an O-, pK of 16, kick out a Cl-, that's a pKa of -7. Huge difference. There is no debate over here. The chlorine is a fantastic leaving group. It's now leaving in this way, and we end up with our product, which is an ester. And this is one of the best, most efficient ways of making esters. And we can, we'll still need to evaluate the other way, the acid catalyzed way. That's the second way that we can ramp up the reactivity of esters. That's going to happen in another lecture. But here we have changed our acid chloride into an ester. And in the lab, this is a fantastic way of doing such things. The key is that we have this really good leaving group. The question, of course, that we have to ask is, well, okay, I've just introduced you to an acid chloride, but how do we make acid chlorides? This is extremely simple. There's one of two ways that you can do it, but you start with the carboxylic acid. So you start off with that over there. And there's one of two reagents that you can use. The one that I prefer to use was thionyl chloride. This is SOCl2. All right, thionyl chloride. I write it there. And that was really my preferred way of doing it in the lab. But there is another way. You can also use phosphorus pentachloride. So that's phosphorus with 5 chlorines on. And if you asked a question like this, you may choose one or the other. All right, don't choose both. That would be just a mess. We want to just use one or the other in order to do that. Okay, I want us to have a look at the mechanism. So what we can do now, I'm going to do this slightly differently from your textbook. It doesn't really matter so much, but you can use either of these two oxygens to use their lone pairs to add to the sulfur. But what we're going to do is we're going to connect the lone pair of electrons of the oxygen onto the sulfur. Why is that happening? Well, the sulfur is extremely electrophilic. We've got these two chlorine groups on both sides of that, electronegative atoms, which are pulling electron density away from sulfur, making it more plus. And we've got an oxygen, which is more electronegative than sulfur, pulling electron density away. So this is an extremely electrophilic center over here. And so we can kick and form a new bond between that sulfur over there. At this point, it would be entirely natural for you to think that the next step that happens is the pi bond on this breaks over here. We break that, and it's then going to come back in and kick out one of those chlorines. It's not going to happen like that because sulfur is actually tetrahedral. And although it looks like a double bond here, this is actually an intermediate. In fact, this kind of thing, which is a sulfoxide, people actually draw not with a double bond sometimes, but actually just with a single bond, and it's an O- and an S+. This is tetrahedral, and because of that, we can do a straight substitution. Now, in this course, if you did this, you broke that bond and you brought it back in and kicked out the chlorine. If you wanted to do that, I'm not going to be too phased at this point. If you do it that way, once you get to third year, yes, that would be a problem. The reason that this is different from a standard carbonyl, this is not a sulfur version of a carbonyl. It's actually, again, it's sp3 hybridized, it's tetrahedral, and so we can do a straight substitution. So when that happens, we can draw out our product. If we just follow everything, we make sure that we draw those arrows correctly. I'm going to stick my H of this H over there, and I'm going to connect to my sulfur, and then we've got the chlorine and the double bond oxygen over there. And so we can follow things. This chlorine that left, I haven't shown yet, was sitting over there. And now we're going to do something which is going to feel pretty odd. And I want us to just keep with me over here, because it's the formation of the products that drives this whole reaction to completion. So just watch what's happening over here. The chlorine is going to act as a nucleophile. This should feel terrible, because chlorine is a terrible nucleophile. But follow what happens here. We break that pi bond over there, and then we end up with an O minus. We've got the chlorine that we added. We've got the oxygen, the sulfur. I'm going to put the chlorine over here, and I'm going to put that there. And I'm just going to switch you're going to see now why. I'm going to switch this H around just to show you the movement of electrons. What happens now is that this kicks back in, and it kicks out an absolutely excellent leaving group, which is this over here. And so this bond breaks, it goes to form a double bond to the sulfur, which means that this bond kicks out a chlorine, very good leaving group, which can pick up this H to form HCl, and this can form over there. So let's just watch all of those different components that have formed. That's going to give us our acid chloride. So that's fine over there. What we have formed over here is SO2 sulfur dioxide, which is a gas, and we formed HCl. So there's an acid that is formed as well in this reaction. And so this gives us our acid chloride. These two things are gases, very stable, and they will escape out of the reaction, driving this reaction to its completion. All right, so this is the way of making acid chlorides, but I said that there's another type of leaving group that we can have that also has a way of superactivating carbonyls, but this one is... we need to learn about it, but it only gets used in kind of very special cases. And I'm going to show you how we make it first, because we're going to use an acid chloride, and then we can have a look at how it's going to react. So the group that we're going to change this into another good leaving group is actually to use a carboxylate. So some other carboxylic acid. It's not a carboxylic acid per se, but it is a carboxylate. This is a very weak nucleophile, and also an okay leaving group, because it has a pK of about 5, so it's relatively low. And so this can add in over there. We break the pi bond, we get the tetrahedral intermediate. I'm going to take the shortcut and bring those electrons back in and kick out the chlorine over there. And so this gives us this intermediate over here, which is called an anhydride. So there's the nucleophile that added over there. So a very weak nucleophile. This thing would never have reacted with an ester. It can only react with an acid chloride. And so we get what is called an anhydride over there. And this part is a very good leaving group. I could color this into green now, and we can do the same sorts of reactions. Let's go and have a look at that. So let's just look at anhydrides, and I'm going to just use, well, what is the most common anhydride, and really, for all intents and purposes, probably the most important one and only one that we really need to look at is acetic anhydride. So this is the structure of acetic anhydride. The abbreviation would be AC2O. And what we essentially have with an anhydride is a carbonyl with a leaving group on it like that over there. So there's our leaving group, which is basically the carboxylate of acetic acid. So it's got a pKa of about 5, which makes it quite a nice leaving group. And what you should notice is, of course, because this molecule is symmetrical, although I said this is the leaving group over here, it could have been this side over here, which is the leaving group as well. Both of these carbonyls are identical. And this reagent that we have over here is one that gets used quite a lot primarily because we can buy it in very large quantities, liters, in fact. And so because it's cheap and readily available, it's used for putting an acetal group, so the AC2O, so this is the O that's over there. This is the acetal group over there on the one side, and this is the other acetal group on the other side over there. So it's two acetal groups, and it's a way of acetylating both alcohols and amines. So we can take an alcohol or we can take an amine, and if we treat it with acetic anhydride, ACT2O, in the presence of a weak base. So it's important just to remember we only need a weak base here, because if we used a strong base, it might react with the acetic anhydride. So the weak base we'd use, I'm going to use triethylamine. I could have also used pyridine here as well. So I'm just making that choice over there. And what we get as a product is the acetylated version. So we would write it out as OAC like that. Or if it's the amine, we would get NaC that looks like that over there. So we switch things around a little bit. This, of course, is the nucleophile. Nucleophilic parts over there, and the AC is our electrophile, the activated ester, effectively, which is reacting. So let's just look at the mechanism of this and try and figure out what's going on and how this works. I'm going to use, we could do it with the alcohol, but I'm going to do it with the amine. Notice it's a nice, that's a good nucleophile, of course. And this reaction, if you take the amine and acetic anhydride in the presence of a weak base, this reaction will happen super quick at room temperature. It'll be over really, really quickly. With an alcohol, take a little bit slower, but actually at room temperature within a few hours, you will have this reaction occurring really nicely. So let's look at that. So what happens is we take our amine and we're going to use its lone pairs of electrons. So we need to draw out our acetate. So there's our acetic anhydride. And we're going to take the lone pair of electrons, and what's going to happen is we're going to add to one of the carbonyls. Either one, it makes a difference. This is symmetrical. And, of course, the pi bond is going to break. And then I'm going to take our shortcut, because we'll get that tetrahedral intermediate, and I don't want to draw it out, so I'm just going to do the shortcut where I'm going to kick the electrons back in and kick out our leaving group like that. And that's an acceptable shortcut, and that basically gets us to the product. So we have the nitrogen. And notice that we still got those two hydrogens that were there. They didn't change. And we have put on our acyl group over there. So I could have drawn a CH3. So this is the nucleophilic part. And we lost our leaving group over here was the carboxylate. So that'll be acetic and acetate that would leave. And at this point, our nitrogen is positively charged, and we can now take our weak base, which is triethylamine, use its lone pair of electrons of the nitrogen to pick up that proton and kick out like that, and that gives us our product over there. So the side products or the byproducts of this are obviously our triethylamine, which is now protonated, so it's triethyl ammonium, and we've got the acetic acetate, which is the carboxylate, as the which was the leading group over there, and that is a salt of a weak acid and a weak base. So in these reactions, and this applies to the acid chloride reaction before as well, and I didn't stress it at that point, it really is important to recognize the role of the weak base. A lot of people, when they do these reactions, make the fundamental mistake of saying that the base deprotonates the alcohol, or the base deprotonates the amine first, generating an O- or an N-, and that does the reaction. And that is completely wrong. This base over here is way too weak. It is impossible for it to deprotonate another amine, because the pKa of this over here is about 35. Whereas this one over here, when it's protonated, is 11. It's just not strong enough. And this one over here is about 16, and this is 11. So it's just not strong enough to deprotonate. It's only strong enough to deprotonate once the reaction has happened, and we've now got a positively charged ammonium over here. This is an amide version of that, so that's actually a lot more acidic. and so it can deprotonate that over there. So in conclusion, what we've looked at is basically reactive versions of this carbonyl group, where we put a good leaving group on there. In the beginning, we had looked at where this was actually quite a bad leaving group, like part of an ester, or a terrible one, like when it's an amide, and how we need to get those reactions to go. But when we put a good leaving group over here, and we've looked at Cl-, very, very common to make the acid chloride, or the carboxylate, so it's an RCOO-, so carboxylate, that would make an anhydride. When we have things like that, these are very good leaving groups, and it allows us to use weak nucleophiles, such as amines and alcohols, which then we can do these reactions under very mild conditions. So far, what we've looked at now is where we are using sort of either a strong nucleophile or a weak nucleophile, and we've got this reaction occurring by making a very good leaving group over here so that the reaction occurs. Our next lecture that we need to look at is how the other way that we can activate this carboxylate over here, or this carboxylic acid type of derivative, I should say, how we can activate it using catalysis, which is another way of activating this carbon group over there. So we'll see that in the next lecture.